Hi, welcome to me313, Mechanical Engineering Thermodynamics. This is a review of Chapter 5, and the topic is the first law for closed systems. So here are the outcomes. At the end of this video, we will have helped you recall what systems are considered open systems. We'll review the first law energy balance for an open system, and then I'm going to wind up just comparing a couple of examples of turbines. So first, let me just remind you what are open systems, and then look at the first system, the energy balance for an open system. And we'll look at some traditional mechanical engineering devices you run into. And what I show here is a pump, and this would be a common open system. And it's open because as the pump is operating, you've usually got material coming into the inlet, going through the centrifugal pump, and then going out. And so if I wanted to do an energy balance, right, I could draw a boundary around it, and I've got material actually crossing the boundary. Here's another example of an open system. This is actually a gas turbine. And so here again, you've got material going through. If this is a gas turbine, maybe it's air. It could also be a steam turbine. You'd have water going through. But again, you've got material going in and out, crossing some sort of system boundary that you have. So again, that would be an open system. And here's one other final one you often run into. A little bit different. This is a heat exchanger, and this is actually a condenser. Or actually what you have is cold water running through these pipes right over here. And then what you also have is some water coming through. Often maybe it's coming in steam that's nearly saturated as a vapor, and then it's actually condensing on these pipes and dribbling out. And so what it's doing is it's transferring heat from this hot stream into this cold stream. But again, if I draw an energy balance around it, I actually have physical material crossing the boundary, and therefore it's going to be an open system. So let's go ahead and just think about any generic open system that I have. And what you would do is you draw a boundary around it and then look at what energy is going in and what energy is going out. And actually, I'm just going to focus on steady state systems for here because that's really what we're going to be interested in the next few chapters in this class. And so in that case, our energy balance is pretty simple. It just says the rate at which energy is going in is the rate at which energy is going out. So you add up all the arrows that go in and then subtract make that equal to all the arrows going out. And so what you've got is you've got work and heat interactions, same ones we saw with closed systems, but now you've got this extra term, which is going to be the material that's crossing it. And to account for the energy required to push it in there, we use the enthalpy to quantify what that is. I'm also showing over here, sometimes you might want to consider the kinetic energy. We actually won't very often, but if you have nozzles, you'd actually want to include this term. But often what happens is these kinetic energy terms are pretty small compared to these other three terms over here, and so we're often able to neglect them. And you'll be able to figure out when to do that. And again, for steady state, those are all going to be equal to a similar set of terms at the outlet. When we're looking at particular devices, usually there's just going to be one of these W or Q terms. For example, if this was a pump, right, there would be a work input required for a pump. If it was a turbine, you might have a work output right over here. So that would be for the turbine. And then usually maybe the other Q's and W's would be 0. Even if you had a heat exchanger, because the heat is actually being exchanged between the fluids, you actually wouldn't have a Q term either. So we'll actually be looking at a lot of systems where we're either going to be looking at the work input or the work output. Often they will be adiabatic, and we'll be able to go ahead and neglect those terms. And so what we'll have is just some W terms, these mass enthalpy terms. And as I said, often we'll be able to neglect the kinetic energy. But I want to remind you, you could have a kinetic energy term in there. So let's just go through a pair of examples, and let's go ahead and look at a turbine. And so let's go ahead and solve this problem here. Where I've got a turbine, I've got some inlet conditions, some outlet conditions. Sorry, I miswrote those. Should be P out and T out. My subscripts were incorrect there. Let's go ahead and say that our material is steam. So this is going to be a water turbine or water system. And since both of these are superheated, I can go ahead and I'll call that steam. But what we'll be doing is using the saturated tables in the back of the book. So go ahead and find these properties. So let's look at our energy balance, and let's just go ahead and reduce it down. And since I've got a turbine, what I'm ultimately going to have in terms of Q's and W's will be this work output term, and then I want to account for the material going in and out. And once again, remember, use enthalpy anytime material crosses the boundary to quantify the energy. So what I've got is my mass flow rate times its enthalpy. So what I need to do is just go ahead and, if I find the enthalpy values, I can go ahead and solve this for what the work being produced is. So what I'll do is I'll go to my saturated tables and just enter this pressure and temperature pair. And this is actually fairly superheated at this point. In fact, this outlet conditions over here are superheated as well. So I'd end up going to superheated tables and just looking up those values. The input value is actually 3457 if I look that up off the table. And the outlet value, and again I got my subscripts wrong, that should say out, H out, that value is about 2819. So I can plug those into my enthalpy values, and let's go ahead and just solve this per mass. So I can just divide through by what the mass flow rate is. This will be how much power this turbine produces per kilogram of water that flows through it. If I put in those two enthalpy values and solve it, I find out that this turbine would produce 638 kilojoules per kilogram of water that goes ahead and flows through there. So if I just increase the flow rate through it, I could actually get more power. Let's look at the exact same example, but in this case, let's go ahead and look at what would happen if instead of this being a water system, this is like a naturally gas-fired turbine. In fact, actually, this picture is a gas-fired turbine. These things right over here are called the cans, and this is actually where the fuel is put in. Usually it's natural gas and is fired. But the bulk of the material going in and out is actually air. So air flowing in here and air coming out here. And so we often neglect that little bit of mass going in associated with the fuel relative to the air. And we'll just look at this as air going in and then some sort of heat input may be going in order to burn that. But if I want to go ahead and find out what the amount of work being produced is, I actually don't need to worry about that Q if I'm told what the outlet temperature is. So maybe these are my conditions. Here, I'll show you exactly. You might have some high pressure and coming in at a fairly high temperature. So what I'm doing now is I'm assuming that I've already heated this up and it's coming out at some other temperature. One thing about gas turbines, and we'll see this later on, is the operating conditions are much higher. They come in very, very hot, and actually the outlet conditions are fairly hot as well. But it's because I've got air here. Remember, air is an ideal gas. So in order to find the enthalpy values, here what I'm going to actually do is just use CPT. So I can go ahead and find out my heat capacity times my temperature. Now I've got a pretty big temperature difference here. I want to account for my temperature variability of CP, and actually the easiest way to do that is just go to table A17, go down and look at your temperature of 1500 C, and just look up that value of H. If you do that, it's about 1973 off of that table, and I can go ahead and plug that in for my H input. And if I come over to the output, and again, looks like I've got all my subscripts still incorrect. Those should all say out. Enthalpy out, and again, I'm going to go to table A17. I'll just now use the 400 degrees Celsius line. Note that table A17 is in Kelvin, so you need to add 273 to it, and you get your outlet enthalpy. So going back to my energy balance, it looks the exact same. The only difference was how I found my values of H for ideal gas. I plug that in, and this one over here is going to produce about 1287 kilojoules per kilogram of air that's moving through. And again, I can kind of neglect the amount of fuel that's happening, just recognizing that that is how this is getting up to 1500 degrees. Okay, well, it's kind of a quick review of steady-state systems, and those are the kind of the concepts that you'll need to know from Chapter 5 as we move through the rest of this class. So, all right, see you later.